Hi everybody, welcome back. This video is going to talk a little bit about protein breakdown. So we've covered about how glucose is broken down. We've also talked a little bit about lipid metabolism, or we'll be covering that soon. We kind of cover those at the same time usually. But in protein breakdown, that's one of our major macronutrients that is part of our diet. And we generally think about protein as being really important for dietary intake because it's used to be a part of a lot of the things in our body. Not only skeletal muscle, but also hormones, our receptors, different signaling proteins as well within the body. We use protein for a lot. So we need to think about when we take that protein into our body through our diet, how do we then convert that protein from a hamburger into insulin, for example? How does one get to the other? Well, let's start by thinking about our 20 common amino acids. We know that we have all of these different formations that are put together to form different proteins. Within these, we have essential and non-essential, ones that can be generated from other amino acids within our body, and ones that are important for us to take in our diet because we cannot make those endogenously within our body. There's also a number of other factors that are associated with these. You can see a little bit up here on our guide, something that tells us about what their polarity is, because that affects how that protein will actually fold, and also things like a branch chain. We'll get into that a little bit later as well when we talk about our protein needs. But if we think about things like leucine being one of the really important proteins that's a branch chain amino acid, how will that potentially affect our ability to form muscle? But if we take these 20 amino acids, we can then combine them into long chains. Here's an example of a chain of cow insulin, for example. We have an alpha chain and a beta chain here. We can see that we have our glycine there. We have our phenylalanine, our valine, different amino acids that are attached to each other in these big long chains. Then those chains are going to be attracted to each other and fold up. If we think about something, an example that we see in our normal daily life, we think about cooking an egg. When we put that egg into the frying pan, the whites of that egg are nice and clear. However, when we add heat to that equation, we're going to denature that protein. We're going to break the bonds that hold it in those folded formations and straighten them out. That's going to cause it to change color and also harden up. So now we know that we start with 20 amino acids, we combine those in different patterns to create all the different proteins within our body, but we still haven't talked about how we break that down to eventually get energy out of it. Well, it starts with our individual amino acids. So let's take this one right here. This is going to be our glutamate. You can see that we have a nice chain of carbons associated with there. And then we also, in this little blue circle, have an H and an N, a hydrogen, and we also have that nitrogen subunit. That's called our amine side group. And important to the use of our amino acids is going to be the removal of that nitrogen. So what do we do with that? Well, we're going to take it off through a process called deamination. And that makes sense. If we're removing that amino side group, well, we're going to deaminate it. And once we do that, we produce alpha keto glutarate plus, you can see that NH4, that's going to be ammonium. And ammonium might sound pretty close to another household cleaning product that you've heard of as ammonia. So NH3 is going to be our ammonia. We have ammonium right here. Pretty close. And if you've ever tried to clean in an enclosed space with ammonia, you know that that fume is toxic to our body. So despite the fact that we need that carbon skeleton of our protein for a number of different uses within our body, we have a toxic subunit that's attached to it. It's not toxic when it's a part of the full amino acid, but when it's left by itself, in larger amounts can be toxic because we're eventually going to turn that ammonium into urea, and then we're going to get rid of it out of our body through a process that we call the glucose-alanine cycle, which we'll get to in a minute. But I wanted to talk about that quickly here because if you think about ammonium to urea, you may have potentially heard of one of the early stages of when we get too much buildup of these nitrogenous subunits in our body. You may know somebody who suffered from a case of gout. Well, that's going to be the buildup of urea in our body in uric acid, which can eventually form crystals, specifically in a lot of your joints. People find it a lot in their fingers, in their toes. In Wyoming, we get a lot of that because where do you get a lot of that urea? Well, you're going to get it from high protein sources, especially after the fall hunting season where people are stocking their fridge with elk. You see a number of cases of gout associated with too much uric acid buildup. And one thing that can potentially exacerbate that is consumption of alcohol, specifically beer. With the reaction between the subunits within the beer and the extra uric acid, you can really put yourself at risk for gout. So that's just a quick little aside, a very Wyoming-specific example there of why we want to be able to get rid of that ammonium. So once we have our alpha-ketoglutarate as a part of our glutamate that we start, what do we do with that? Well, here's a picture of our good old friend, the Krebs cycle. And you can see right over here, here is our glutamate. What do we do with that glutamate? Well, we can then convert it into alpha-ketoglutarate, just like we talked about, and that then becomes a part of our citric acid cycle. You can make some ATP there. You're also going to create your electron carriers from that and move it into the electron transport chain. Fantastic. If you look at these lists in the boxes up here, you can see that our different amino acids are going to enter into the Krebs cycle in a number of different locations. Everywhere from creation of pyruvate, we can make some acetyl-CoA. We can also make our oxalo acetate, our fumarate, our succinyl-CoA, and our alpha-ketoglutarate. And you can also see that we have, look at this, our arginine, proline, histidine, histidine and glutamine, which all are converted into glutamate. What's going on there? Well, if we think about this, this occurs through a process called transamination. And I already discussed deamination, or the removal of that nitrogen. We can also go through a process where we take one amino acid and move the amine group to a different location and create a different amino acid. So if we move that amine group, that's going to be transamination, whereas if we remove it, it's going to be deamination. All right, so now we've covered how we get that amino acid into our body, how we take that big protein, break it down into the individual amino acids. Once they're individual amino acids, we take that nitrogen off. Now that carbon skeleton can enter into the Krebs cycle and create some ATP. Because even at rest, about 5% of our energy is through the metabolism of protein. So we have to make sure that we have the ability to form ATP from this. And when we start exercising, that percentage is going to go up a little bit. But remember, the byproduct of this protein metabolism is going to be that amine group. So now we have to finish up with covering what happens and how do we get that amine group out of our body. So let's go to our final picture here of our alanine glucose cycle. Let me write that right up here. And we have a nice silhouette, I believe, of my bicep right here. And we also have our liver. So I'm just going to put skeletal muscle. And liver. And these areas are going to be important for the removal of that nitrogen. So let's start over in the muscle with our amino acid. There's our amino acid. If we wanted to break that down, remember, we're going to get, let me draw a nice long line here to get a lot of room. We're going to get our carbon skeleton. We're going to then be able to take that, enter it into the TCA cycle, which makes ATP, and that makes us happy. Okay? So after we have that ATP, nice smiley face there, what happens to our amine group, our NH4? Okay? Well, we need to combine that with pyruvate. Oops, let's move down just a little bit. If we combine our ammonium with pyruvate, that's going to create glutamate. And I know I'm going out of our muscle a little bit, but now, so let's take our pyruvate plus our ammonium is going to make glutamate. Glutamate can then be converted into alanine. The great thing about alanine is that can be safely transported. Remember, we have that toxic subunit right there. Alanine can be safely transported in the bloodstream. So now, let's draw ourselves a nice blood vessel, just like we have in our body, that goes directly from our bicep right to our liver. Here we go. Just like everybody has, they have that one artery that goes right from their bicep to the liver. Not really, but for the purposes of this example, we'll just say we're going to move that alanine into our liver. Once that alanine is here, what do we need to do? Well, we need to get rid of that nitrogen. So we'll break it back into glutamate, or transaminate it back into glutamate. Where now we can remove the ammonium. Then ammonium will then go into the urea cycle. And be moved from the kidney, or moved from the liver to the kidney for excretion. Hooray! We've gotten rid of our ammonia. Fantastic. We've protected ourselves and gotten rid of that ammonia. But remember, from that glutamate, we're also going to have our other subunit. If you look back over here, what do we use? We had our ammonium, we had our pyruvate. Now we're breaking down our glutamate. We're going to make our pyruvate. Through gluconeogenesis, we can make our glucose from that. Back in our liver, now we can take our other blood vessel right back to our muscle. We can take that glucose, move it back into the muscle, which can also, through the process of glycolysis, get back to the citric acid cycle, where we will then make more pyruvate, and this is how it becomes a cycle. Okay? We have our amino acid that we started with. We break it into its subunits, our amine group right here, which is going to be our ammonium. We use the carbon skeleton in the citric acid cycle to create ATP and our electron carriers for the electron transport chain, but we got to get rid of that ammonia. So we combine it with pyruvate, make some glutamate, make some alanine. Remember, it's the alanine glucose cycle. The alanine safely transports through the bloodstream to the liver, where it gets reconverted, transaminated back into glutamate. We can, in the liver, now create our urea. The urea goes to the kidney. We can then move it into the bladder and get rid of it through our urinary tract. Also, that pyruvate goes through gluconeogenesis to glucose, back through the bloodstream to the muscle to provide more substrate for ATP production. So, I know this has been a little bit of a longer and drawn out video, but we started with consumption of protein. We take that big ball of amino acids, break it into the individual subunits. Then, with that individual subunit, we can cleave off the amine group, take that carbon skeleton, move it into the citric acid cycle, and now through the process of the alanine glucose cycle, we can safely get rid of that urea and the ammonia associated with that. All right, stay tuned for more lectures about macronutrient metabolism.